So let's see, here we are. We are last section of the chapter. I'm going to abbreviate part of it. I apologize for being late to deliver the video. Just a busy day at work and a busy day at home. So here we go. This is section 10.6. It's called Construct and Interpret Binomial Distributions. A whole bunch of vocab, pretty interesting. I'm going to kind of skip it. You're welcome to read over it. The binomial distribution, we'll get into in detail. Binomial experiments kind of similar, tied together. Symmetric when we talk about a histogram, and we will look at the histogram of our dice data, which I forgot to show you, or didn't think it was important at the time, but it'll be nice to look at, so we'll go back and look at it. So the first thing here, this is very similar to our data. I thought I'd show you. One, I never realized there is such thing as a four-sided dice or die. It looks like a triangular. It looks like a pyramid basically, and it does work. So feel free to look one up on Google, as I did, and you'll see that they do exist. And so the way it lands, the sum of two of those die could be anywhere from 1 to a total of 8, because the highest value are 4s. And so you see this nice histogram. This is a distribution. So how frequently do you get 5s? And it looks like your probability here is 1 out of 8, or 1/4. So they have a nice table. So I thought I'd go back to our data, which is here in numbers. And there was our data, or your data. I didn't really do anything. I didn't roll any die. But here, again, we saw what the probability should have been, or should be, right, for rolling a die. And then this is what you guys got by rolling 901 times. And so you see here, this is kind of an experimental probability. So this, we would have expected perfect symmetry. You do see the symmetry. We expected that the 7 would have been the highest, but in our case, it was quite a bit off, right? The probability of rolling a 7 is 16.7%, and we only had 13.4. And again, that's real life. That's kind of what makes probability and what's actually gonna, I'm probably gonna, I don't know, the probability of something happening and it actually happening aren't the same. It's just the likelihood that it would happen. But again, with our 900 rolls, we do see a nice histogram here of what happened. And again, back to our spreadsheet, this would be this is theoretical probability. This is what it should be in our histogram. I could make a histogram certainly of that theoretical, which I'll do right now. Just I can show you and make a chart and a histogram. And there's the histogram. This is the theoretical probability versus what we saw here, which we can compare the two, right? The theoretical versus the your actual data versus what it should have been. But again, beautiful, right? I mean, really spectacular how we are so close. So very interesting, very nice. So switching gears slightly, we also want to talk about what's called the binomial experiment. So this only happens, you can only use this formula, and look at that formula down there. Wow, right? So we use the combination. I have to get my pen. Sorry about that. We have to use combinations. A little off my game. Sorry. So we use combinations, or NC, right? Then the next thing is we have the probability of the event that we're interested in raised to however many times we do it, and the probability of that event not occurring. So, sorry, let me back up a second. So we can only do the binomial experiment when we have independent trials. So basically one event doesn't affect the next event. This is kind of like, hey, let's say I'm a 50% free throw shooter, and every time I get to the free throw line, it has no, theoretically would make no difference what I did the last time. Of course, psychologically that may not be true. Each trial has only 2 possible outcomes, either success or failure, true or false, right or wrong. I mean, these, again, only 2 possible outcomes. And the probability of success is the same for each trial. And that probability that you're interested in is P, and the probability of it not happening is, of course, 100% minus that probability. and then you get to use this formula. So here the next example, and then we're done with the video. So again, short video. My apologies for not posting it earlier. But here's an interesting one where you can say the survey taken at your school found that 68% of students are not afraid to fly. So that means that 32% are afraid to fly. And that's it. There's only two possible outcomes, kind of like heads, tails, true, false, right, wrong, make it, miss it. That's when you can use a binomial experiment. Suppose you randomly survey 5 students, draw a histogram of the distribution. So really, this binomial experiment is what I'd like to think about. So this first case, this is, hey, of the 5 students you survey, none of them, none of them are not afraid to fly. That sounded kind of weird to say it. But again, here, 0 kids are afraid to fly. And so you'd set up this 5C0, take the probability of what you're interested in, raise the power 0. But then, of course, you've got to have 5 students that are afraid to fly. Does that make sense? And so here now we do the probability of 1 of the 5 kids that you asked about would be afraid of flying, and the probability would be 5C1 times the probability of that person not being afraid to fly, and then times the probability that of the other 4 students that you picked that are afraid to fly, and that that's about 3.6%. And so what's interesting, you start to see like the way this falls out, that more than likely, the highest probability is that you're going to get 4 students that are not afraid to fly and 1 that is. So again, this formula is a little tricky. We're gonna have some problems in class that I think if you get into the routine, you'll see how this formula works. Again, the first time I opened this, I said, "Whoa, what's going on here?" So again, if you wrote very little notes on your note sheet today, no problem. Again, I'll get you more familiar with it with the problems tomorrow in class. And again, hopefully you really enjoyed seeing your histogram from the rolling dice data. And again, I apologize for being so late on the video. I look forward to seeing you tomorrow.